In this part, I'll start with a recap of what we discussed in the last class. Then I'll take one example. After that, I will take conformation of radiation from the Hertzian dipole. Then I will take power radiated, then near fields. After that, the power in the near field. Then we'll consider what is called Radian sphere. Then we'll consider lines of forces. Finally, a pseudo Matlab code, so that people can write a Matlab code for lines of forces. So this is the outline for today's lecture. Let us start with recap. Last class, we saw that for time harmonic field, A is also time harmonic, phi is also time harmonic, which means vector and scalar potentials are time harmonic, so that the vector potential or the scalar potential both can be represented as an integration of the current distribution or charge distribution over a closed volume. So that distribution into e to the power minus jkr by r. That comes from the Green's function. 1 by 4 pi, of course, will be there. Then we saw that once we go to time harmonic field, the Lorentz condition becomes simplified. The Lorentz condition now becomes divergence of A is equal to minus j omega epsilon mu phi. Using that, the equation, time domain equation for the vector field reduces to a simple wave equation, del square AR plus k square AR is equal to minus mu JR. That can be solved by starting with a delta function or impulse function on the right hand side, from which we find the Green's function as g is equal to exponential minus jkr over 4 pi r, and using this g we can find out the vector potential as integration over the volume and convolution of j and g. So once we find out A, we can find out what is H, or the magnetic field, as 1 upon mu curl of A. Then we can find out E as 1 upon j omega mu epsilon into divergence of gradient of divergence of A plus k square A, where k square is equal to omega square mu epsilon. K square is equal to omega square mu epsilon. Similarly, we can find out the scalar potential phi. Then we looked at the polarization inside a material medium. We defined the polarization if it is of a time harmonic nature. Then we defined the polarization to be P is equal to small p into impulse at r, because we took dou by dou t as a j omega t. Using that, the total polarized current becomes j omega p, then impulse of r, impulse at r. Similarly, rho becomes minus p dot grad of the impulse function. So using this, we can find out A, or the vector potential for a material medium, polarized material medium, as j omega mu 0 p gr. Gr we have found out, exponential minus jkr by 4 pi r. So we can place that, or in short we can write gr. Similarly, phi r can be found out as divergence of A over j omega mu 0 epsilon 0. Once we are equipped with A and phi, then we can find out H as minus j omega p cross grad of G. Similarly, we can find out E as 1 upon epsilon 0 grad of P dot del plus K square P whole into G. So this is what we found out in the last class. Then we proceeded to find out explicit expressions for H and E. Accordingly, we found that H is equal to j omega into jkr plus 1 by r into p cross r cap gr. E is equal to 1 by j omega epsilon 0 curl of j omega into jk plus 1 by r p cross r cap gr. So finally, p is simplified to 1 upon epsilon 0 jk plus 1 by r, they remained outside. Then vector operations, vector differential operations took place. So that gave me 3r cap r dash dot p minus p over r into gr plus k square by epsilon 0 r cap cross p cross r cap gr. This was left as a homework for you. I hope you have been able to solve this. If not, I think you can solve this in a short period of time in future. Now this gave us the total electric field and magnetic field. From that, we eliminated the portions which are varying as 1 by r square or 1 by r cube, since they belong to the near field. We are interested only in the radiation field or the far field. Therefore, we found out expressions for HRAD and ERAD, which vary as 1 by R. So we found out HRAD is equal to K square by eta 0 epsilon 0 R cap cross P exponential minus JKR by 4 pi R. So here you can see only 1 by R variation. Similarly, ERAD is equal to K square by epsilon 0 R cap cross P cross R cap into exponential minus JKR by 4 pi R. Now, if we compare these two, HRAD and ERAD, we saw that eta 0 HRAD is equal to R cap ERAD, or there is a relationship between HRAD and ERAD, which is by eta 0. So ERAD is eta 0 times more than HRAD. So in terms of magnitude, ERAD will be eta 0 times more than HRAD, but which is 120 pi times more than HRAD, or 300 approximately 377 ohms times HRAD in terms of magnitude only. Otherwise, variation etc. will be different, but magnitude will be this. Therefore, if anybody is interested in simulating electric fields and magnetic fields, particularly in FDTD, finite difference time domain technique, they must remember this in mind. Otherwise, E will be so small compared to H that it will be very difficult to simulate it or see whatever is the result. So now let us move to a Hertzian dipole example. So what we have done is, we have in nutshell up to now we discussed what we discussed in the last class. So now let us look at a example. This example gives us an explicit expression for the fields when the polarization P is z directed and it is oscillating as cos omega t. Time harmonic is cos omega t. So in terms of time, it is varying as cos omega t and it is z directed. Earlier what we saw, P is equal to P into e to the power j omega t. Now if we compare these two, e to the power j omega t and cos omega t, they are related. What is the relation? Cos omega t is a real part of e to the power j omega t. So we have not done any mistake, but what we have to do is whatever we have done, that we have to now reconsider by taking a real part. The expressions we will find out the real part that will give this. Now this is a historically important problem. Why it is? What is the history behind this? The history comes from Heinrich Hertz itself. He was a scientist par excellence, as I discussed in the last class. He was very strong in experiments. He was equally strong in theory. Therefore, we saw today the Maxwell's equation in compact form as 4 equations. That was his contribution. So he also tried, once he was confirmed that there exist electromagnetic waves, he tried to find it out theoretically. So this problem was first considered by Heinrich Hertz in one of his papers in 1889. Remember, 1887 was the experiment. 1889 is the theory confirming the experiment that came from Hertz. Now, he thought that if it is working as a wave, then we can always see a wave. How do you imagine a wave? Throw a stone or a pebble to still water, then you will see that from the point of strike of the stone or pebble on still water, waves are emanating outward radially. That is what you can see in this simulation. So waves are emanating outward radially. Here it is not still water, but free space. Instead of stone, there is a dipole, Hertzian dipole, a small dipole. So this is all his publications were later compiled into a book by Davour. So Davour publication compiled them into a book in 1962. This book is available in Google Books for free. So you can download it and read it. I will advise you to go through this book if you are interested. You will get many interesting things about Hertz and his work. I think I also gave you the link for the Google Books. Now let us come to what we had seen in the last class. This I have already discussed. We found out H is equal to j omega whole into j kr plus 1 upon r p cross r cap gr. Similarly, we found out an expression for E. I am not repeating this. Just remember that we found out an expression for E. Now what we have to do? We have to find out the real parts of this. H and E, we have to find out the real parts because e to the power j omega t is now cos omega t. How do we do this? So that we can do by starting with a replacement. First replacement is take P is equal to Pz e to the power j omega t, real part of that. If we take P is equal to Pz cap e to the power j omega t, then we also consider the time variation for the Green's function grt. Then for time variation, we will multiply e to the power j omega t. So this expression ultimately becomes 1 upon 4 pi r into cos kr minus omega t minus j sin kr minus omega t. This you know, e to the power j theta is equal to cos theta plus j sin theta, and e to the power minus j theta is equal to cos theta minus j sin theta. This second identity of Euler is used here. So once we know this, then write this j omega into jk plus 1 upon r. This can be replaced as minus omega k j into j minus 1. So minus omega k plus j omega upon r. So that is one thing. So now multiply that with gr. So j omega jk plus 1 by r into gr, because that is what is occurring in H and E. In both the cases, we have this term j omega jk plus 1 by r gr. So if we multiply that, then on the right hand side, what we will get? 1 by 4 pi epsilon cos minus j sine into minus omega k plus j omega by r. So from that, what we will get? We will get the real part of this as p into omega minus k cos kr minus omega t plus sin kr minus omega t upon r. Similarly, for the E, we don't have j omega, but instead of j omega, we have 1 by epsilon 0. So put 1 by epsilon 0, take the real part. So that will give you P into k sin kr minus omega t plus cos kr minus omega t by r. So these replacements are to be made in the fields of H and I, for the H and I field. So if we make these replacements, what we will get? Expression for E and H. Expression for E with these replacements becomes ER is equal to P k sin kr minus omega t plus cos kr minus omega t by r whole into 3r r dot z minus z divided by 4 pi epsilon 0 r square. These j's are actually z caps. I don't know why I cannot see the caps here. Plus pk square r cap cross z cap cross r cap divided by 4 pi epsilon 0 r into cos kr minus omega t. Similarly, for HR, we will get the same term, P omega, the first term and the second term. Last term is not there, but for the 1 by 4 pi epsilon 0 r square term, we have z cap cross r cap upon 4 pi r. So now we found out E field and H field. Now use in this, you have to use some other things. So what you will use is z cap is equal to r cap cos theta minus theta cap sin theta. I hope you remember this from the spherical coordinate systems if you have studied it earlier. Otherwise, try to remember this way. Now, if you look at the spherical coordinate system, r is going out in the radial direction or along the r direction, we have got r cap. Then on the sphere, from the z axis towards the x axis is the theta cap. So they are in that direction. And on the x plane or along the x plane is the phi cap. R cap, phi cap, theta cap are orthogonal to each other. Now, if you have an element along z, which is the current element, that will make an angle theta with r cap. So, along r cap, the component will be r cos theta. So, therefore, z cap is equal to r cap cos theta. Then, along phi, there will be no component because it is symmetrical in phi, there will be no component. Along theta, you will get the sin theta component, but here it will be in the negative direction because it is moved, the theta cap is in towards the xy plane. So it is in the therefore it will be in the negative direction. So you will get z cap is equal to r cap cos theta minus theta cap sin theta. So from that you can find out easily r cap dot z cap. So just take dot product, r dot r will exist, r dot theta will be 0. So that will give you cos theta. Similarly, find out what will be the cross product z cap cross r cap. That will give you minus phi cap sin theta, because z cap we know r cap minus theta cap. So that cross r cap cross r cap 0 minus theta cap cross r cap, that gives you minus phi cap. So minus phi cap sin theta. Then find out the triple product r cap cross z cap r cap. Now we know what is r cap, then we know what is z cap cross r cap. So this will be r cap cross minus phi cap sin theta. R cap cross phi cap is equal to theta cap. So this will give you minus theta cap sin theta. So now we know all the terms that are appearing in ER and HR. Therefore, what we can do is find out the final expressions for ER and HR. So finally, using those terms, you will find out ER as P into K sin KR minus omega t plus cos KR minus omega t upon R whole into 2 cos theta by 4 pi epsilon 0 R square. Similarly, we will find out E theta is equal to P into K sin KR minus omega t plus cos KR minus omega t upon R. So that part, bracketed part, remains unchanged. Then sin theta divided by 4 pi epsilon 0 R square. Then we have an additional term, that is minus pk square sin theta upon 4 pi epsilon 0 R into cos KR minus omega t. Now compare these two terms. If you compare these two terms, what is the difference? The first one has only R square and R cube component, whereas the second one has only R component. No, second one has dominant R component as well as it has R square and R cube component. We will discuss these sometimes later in today's lecture, the physical significance of what happens because of this. I think I had briefly discussed their significance, that if RQ and R square are dominant, it is near field. Why it is near field, that we discussed. And if they are not dominant, it is far field. But this we will discuss. But just remember these equations. We will discuss this later. Similarly, HP will become same. The first part will remain as it is. Only thing is, we'll multiply an omega, and sine will become cosine, because H, how we are finding H? E and H are related by curl or a differentiation. So sine will become cos minus cos. Similarly, cos will become sine. So that remains as it is. We are differentiated it with respect to time. Therefore, minus omega comes outside. So that becomes P omega. And the second term remains as it is. Sin theta becomes, cos theta becomes sin theta, 4 pi r. So 2 cancel. 2 will be there. So 4 pi r. Epsilon 0 r square is not there when you are considering phi. Then we can see eta 0. If we compare these two, then we'll see eta 0 is equal to eta 0 h phi is equal to E theta. Let me give that as a homework to you. So the homework is, so that in the radiation zone, the fields for a Hertzian dipole can also be expressed as E is equal to P upon 4 pi j omega mu e to the power minus j k r upon r sin theta theta cap. So this is E theta. Similarly, H is equal to P upon 4 pi j k e to the power minus j k r by r sin theta phi cap. In theta, both are varying as sin theta. E is along theta, H is along phi. So they are orthogonal to each other. If they are orthogonal to each other, then their cross product will be along R, which means the power will be radiated along that we'll see later. But if we compare the magnitude of these two, that will give me eta 0 into h phi is equal to E theta. Now this is a very interesting thing. I hope you remember when we discussed about this point dipole in the initial part, I said that it is a spherical wave. The wave front is spherical. Now, in the far field, something interesting happens. In the far field, eta 0 h phi is equal to E theta, or eta 0 h is equal to E. The far field fields are h phi and E theta. So in the far field, I will say it is eta 0 h is equal to E. Now this is a condition which is satisfied for plane waves. We started with spherical waves, but as we go to far field or the radiation field, the spherical waves become plane waves. So the radiated field from an antenna in the radiation zone or in the radiated field behaves like a plane wave, although it is theoretically a spherical wave. In the far field, it behaves like a plane wave. Now you can ask me why this happens. What is the reason behind this? You all know from the school days or college days that if I take a sphere of very large radius and consider a small portion on its surface, that portion will not look spherical to me. It will look like a plane, normal plane. For example, consider the surface of the earth. We don't find the surface of the earth to be spherical. To us, it appears as a plane. Right? The same thing happens to the radiated fields as we go to the radiation zone or to the far field region. It appears for all practical purpose, the fields behave like plane waves. Now let us try to confirm whether there is actually radiation or not. We found the fields, etc., and terms for the fields, etc. Then let us consider whether there is actual radiation or not. Now, I will concentrate only on the radiation field or radiated zone. If I go to the radiated zone and find that there is some power, then I will say that, okay, there is actually radiation. So for how do you find out power? The power density comes from the Poynting vector. So let me find out the Poynting vector for this. So S is equal to E cross H star 1 upon 2. So 1 upon 2 remains as it is. Now I'll put the expressions for E and expression for H star. So you can see that 1 by 2 is there, P square by 4 pi, that is common in both the cases, but P by them P square by 4 pi square that becomes, so P by 4 pi square. Then for E, it is j omega e to the power minus j k r by r sin theta theta cap. For H, we do not expect now minus j k r because H is the complex conjugate. So it will be j k r. Similarly, for jk becomes minus jk. So that is what has happened for the H. So now if I multiply them, then what I will get? Theta cap cross phi cap. That gives me r cap. Rest will be 1 by 2 p by 4 pi whole square. And if I multiply them, they will cancel out. E to the power minus jkr cancels out. Right? Then r into r becomes r square sine square theta. Okay, so everything goes out. So I am left with 1 by 2 p upon 4 pi whole square omega mu k. From where we are getting omega mu k? j omega mu into minus jk. So j minus j1 omega mu k sine square theta upon r square into r cap. So that gives me the S. Now, what does this imply? It implies that S is real value. Then it is radially directed, radially outward. It is not inward. It is radially outward, which means power is going out from the source. Now here I have given you an animation which shows that at the center along the z direction is my antenna. I don't know whether you can see the antenna clearly here or not, because antenna is the Hertzian dipole. It's very small. I have put the antenna there, but it is very small. Now, what is evident from it is that the the current in the antenna is increasing, then it is decreasing. So it is oscillating. As it goes up, it is increasing. As it goes down, it is decreasing, which is it is oscillating. As it is oscillating, the fields are gradually emanating out from the dipole. So in fact, it is going out along the R, right? So radially they are going out. That is what I am seeing here in the animation. We will consider a similar animation later. Now look at the plane, XY plane, which is in the bottom. If you look at the XY plane, which in the bottom, you can see the electric lines of forces which are going out from the dipole or from the Hertzian dipole that I am considering. This I will consider later in detail how to get this. At least I should make you conversant or convenient in writing a program for the contours that you are seeing on the bottom. So these are radially directed fields. So this confirms that there is power which is radiating out in the radial direction. Now let us quantify the power. So we'll find out what will the total radiated power. Right, power density we have found out. Now we'll find out the total radiated power. How do we find out the total radiated power? We integrate the power density over the volume. Now in this case, we are considering only the surface. So instead of integrating over the volume, we will integrate it over the surface. So integrate over the surface area. So S dot dA, A is the surface area. So S dot dA integration will give me the total power, radiated power. So that will be 1 by 2 P upon 4 pi whole square. For S, I am writing the expression. Then omega mu k integration dA is equal to r square sine theta d theta. There is no r square in this case. So sine theta d phi. D phi is from 0 to 2 pi. So 0 to 2 pi d phi into sine theta d theta. For S, I have got a sine square. So that gives me 0 to pi sine q theta d theta. Integrate sine q theta d theta. It's simple. That will give you 4 upon 3, 4 by 3. And integration of d phi 0 to 2 pi gives you 2 pi. So the last two terms are 2 pi into 4 by 3. First three terms remain as it is. So if I multiply them everything, that will give me omega mu k upon 12 pi into p square. So I have now quantified the power being radiated. So this is the power which is distributed over the spherical surface, whole surface. This is the power that is distributed. So this is the total radiated power. Now you can see there is no imaginary term. So the power is real. Radiated power is real. That means If the power is real, it means there is a dissipation of power from the antenna. If there is an imaginary component, then there is some storage. Here there is no imaginary component, which indicates that there is a dissipation of power. So power is real and therefore it is dissipation. Second important thing that you can mark is the power, radiated power is independent upon R. There is no R term here. That means if I integrate it radius, I can get the radiated power. So it is independent upon R because due to integration over a sphere of large radius. So this gives me the same total power irrespective of radius. As I keep on increasing R, I will get this power. Now why I called it a over a sphere of large radius? If it is a small radius, what will happen? If R is small, we will be within the near field. There is a possibility of being within the near field. In that case, there will be no radiation. So there will be no radiated power explicitly. There will be other powers also. Therefore, this expression for radiated power will not hold there. Therefore, I said it is over a large radius. Now, this is usually referred as the radiated power. This power is referred as the very large distance. Now, what happens if we are not at a large distance? If we are in the near field. So, for that, let us find out the expressions for near field. So, the near field expressions will be this HNF. NF is for near field. HNF will be P upon 4 pi e to the power minus j kr upon r square sin theta phi cap. Similarly, you can find out ENF from the value of what will be ENF. Now, let me tell you something. What the what is indicated here? It indicates that the general field expressions are valid at any distance from the Hertzian dipole, whether it is near field or it is far field, and are important in some applications for understanding the input impedance of a dipole. That is why I am going to look into this. Near field is mostly associated with the input impedance of the dipole. Why it is associated with the input impedance? Because it is the stored field. If it is the stored field, then the electric field components are, look at the electric field components, they are in phase, right? Electric field components have, electric field has two components, theta component and r component, and they are in phase. Look at the denominator, there is a k term. Both of them contain k term. Therefore, it is in phase quadrature. They are in phase, right? But so the energy is interchanged between these fields with time. Because they are in phase, the energy will interchange between them in time. At one instance of time, the electric fields are strong near the dipole, close to the maximum charge region. This is what you saw in the previous animation. Then at a instant of time, which is quarter period, so in that case, after quarter period later, the energy will be stored in the magnetic fields. So they will decrease. So peak will go down. They are stored in the magnetic field. They will be primarily close to the center of the dipole where the current is the maximum. Remember this, current is maximum at the center. Current has to be zero at the two ends because they are open circuited. So voltage will be maximum or E will be maximum at the two ends. So this is what happens. Now E and H, if you compare E and H, they are actually in phase quadrature. In the H, look at the denominator, there is a 4 pi, but in E, it is 4 pi k, which means they are in phase quadrature. Why I am saying they are in phase quadrature? K is equal to 2 pi by lambda. You know that. And you also know that phase difference is equal to 2 pi by lambda path difference. So there is a relationship between phase and path. Right? So that now we are adding by k, we are adding 2 pi by lambda, which means there is a phase difference between H and E. How much phase difference? It is 90 degrees because it is lambda by 2, so that gives you 90 degrees. So E and H are in phase quadrature. Now once we find out these near fields, then let us find out what will the power there. There can be some power in the near fields. So let us find out power. How to find out power? First find out the power density. Power density for the near field will be following the same expression, 1 by 2 E cross H star. Here it will be E near field cross H near field star. So that will be equal to 1 by 2 E NF theta H NF star phi r cap minus E NF r H NF star phi theta cap. Here we will have two components, r cap and theta cap. In the previous case, we had only one component, r cap. Now we have additional theta cap. Not only that, once we multiply that, the whole thing contains a j component. So that becomes minus j eta upon 2 pi, p by 4 pi square, then whatever is there. Left, all other terms are there. So the whole thing is imaginary. SNF has a imaginary power density. So in the near field, the power density is imaginary in nature. If it becomes imaginary, there will be no radiation. When it will become imaginary, whatever you are sending is coming back. So they are adding in phase. So they are forming standing waves. So imaginary power density indicates standing waves. So rather than having a traveling wave, we are having pure standing waves in the near field. So there is no radiation in this case. So energy is stored. Now how energy can be stored? Energy, we know, reactive devices store energy. Therefore, in this case also, the energy is stored as if it is working as a reactive device. Like in a reactive device, energy is stored. So antenna impedance component will have a reactive part. So antenna input will have a reactive part associated to it. What happens to the real part? Reactive part means imaginary part. What happens to the real part? The real part of the input impedance actually represents the radiation. If ohmic losses on the antenna structure are neglected. So neglecting the ohmic losses in the antenna structure, the real part is the radiation from which we get the RRAD, radiation resistance. Okay, so that is sometimes we will consider what happens to the power in the near field. Now we saw this, we have got imaginary power, and in addition to this, we also have the radiated power. Although it is not radiating, although it is not dominant, the radiated power is not dominant, but it is still there. So let us consider something called Radian sphere. Considering this, what is a Radian sphere? This brings into account the radiation power density even within the near field. This exists everywhere. The near field power does not exist everywhere. Radiation power density, it exists everywhere. It passes through the near field. So in the near field, this is also there, which means the distance of maximum radiation power can be obtained if you consider this. Now where that will occur? That will occur if Kr is equal to 1. You know K is equal to 2 pi by lambda. So 2 pi by lambda R is equal to 1. That gives me R is equal to lambda by 2 pi. So if R is equal to lambda by 2 pi, then we'll get the distance of maximum power radiation. Now what happens at that point? Consider the total field. In the total field, if I take Kr is equal to 1, then the contribution due to each part, each has a 1 by Kr, 1 by Kr square, or 1 by Kr cube, 1 by R square, 1 by R cube total. Now this becomes 1. R becomes 1 in terms of lambda. So if R is equal to 1, R square, R cube, R all are 1. So their contributions becomes same. So this is the point. Kr is equal to 1 is the point where all of them are contributing equally. If I come below that point, which means if my R is less than that, then I get reactive powers. Right? But at Kr is equal to 1, my reactive power is equal to the radiative power. So interior to this radius, if I come interior to this radius, I will get reactive power, dominant reactive power. If I go exterior to this radius, I will get dominant radiative power. Therefore, if I imagine a sphere at Kr is equal to 1, so the region enclosed by that sphere, including the surface, is called the radian sphere. So please remember this. That is what is called the radian sphere. So within the radian sphere, near field is dominant. Outside the radian sphere, far field is dominant, or radiating field is dominant. This is actually used when we define the near field and far field. If you remember, I said that far field occurs when R is greater than how much? Now I told you, just now I told you how much. R is greater than Kr is equal to 1. R is equal to 1 by K. 1 by K is 2 pi by lambda, or lambda by 2 pi. 1 by 2 pi is 1 by 6, approximately 1 by 6, right? 1 by 6 is 0.66. So that is what I have told you. When R is greater than 0.66 lambda, approximately 0.66 lambda or 61 lambda. When we discussed near field and far field, that is what I have told you. Now let us consider what will be the lines of forces. Lines of forces will have azimuthal symmetry in phi. So they are symmetric in phi, so I am not worried about the phi, because it is having azimuthal symmetry in phi. My plane of interest will be phi is equal to 0. That is the xy plane. In the xy plane, I will find out how the lines of forces will appear. Okay. Now, we know E field is tangential to the lines of forces. So each E field is tangential to its corresponding lines of force. Therefore, at any point, a small displacement along dr will be a tangent to the line of force, because E is tangential. So along dr, or along a small displacement along r of amount dr will be tangential, or will be tangent to a line of force. If it is tangent to a line of force, then this tangent will be parallel to E. So if this is parallel to E, then dr cross E is equal to 0. Two parallel vectors, their cross product is 0. So dr cross E will be equal to 0. So at any point, dr cross E is equal to 0. What is its significance? The significance is now we can use this property to find out the lines of forces or to determine the lines of forces. This is the significance of knowing E and its lines of forces are tangential to each other. Okay. Now let us find out what happens. We said dr cross E is equal to 0. Find out what is dr cross E. So dr cross E is equal to dr is r cap dr plus theta cap r d theta. Put that r cap dr plus theta cap r d theta. E has two components, r component and theta component. So r cap er plus theta cap e theta. Take the cross product. If I take the cross product, that will give me phi cap dr e theta minus r d theta er. Now what will be that? I know dr cross E is equal to 0. So for that I put 0. Right hand side C is equal to 0. Phi cap is not equal to 0. So if phi cap is not equal to 0, from this equation what I will get? dr upon d theta is equal to r er upon theta. Right? Which means now r is a function of theta. So using this, we have converted r to be a function of theta. Right? This is going to be useful in finding polar representation of the line curve. Line curve means field line curves. Right? So now let us solve these equations, whatever equations we have got. dr by d theta is equal to r er upon theta. So let us try to solve those equations. How we'll solve those equations? Start with using some dimensionless variables. So I will define these dimensionless variables. Let me take alpha is equal to k into r. K is equal to 2 pi by lambda. So it has dimension of inverse of L. R dimension is L. So alpha is dimensionless. Xi is equal to omega t. Omega is equal to 2 pi f. F is equal to 1 by t. So t upon capital T, that is dimensionless. So xi is dimensionless. Similarly, you can see minus E0 is equal to pkq by 4 pi epsilon 0. Kq, p into kq by 4 pi by epsilon 0. That also is a dimensionless quantity. So all these are dimensionless variables. So I will replace these in the original equations. If I replace this, my ER becomes E0 2 cos theta by alpha square sine of alpha minus g plus cos of alpha minus j by alpha. So this is my ER. Similarly, E theta is equal to minus E0 sine theta by alpha whole into cos alpha minus zeta minus cos alpha minus zeta by alpha square minus sine alpha minus zeta by alpha. You can easily find it out. Simply replace this. So from that, I will define a simple thing. Let me define psi alpha is equal to sine of alpha minus zeta plus cos of alpha minus zeta by alpha. This is in the bracketed term in the previous equation for E, or it is in the term for H within the bracket. Now if I take its derivative, so d psi by d alpha with respect to alpha, so my psi dash d psi by d alpha, you can write psi dash for simplicity or for compactness, I will use that letter. So this will be equal to, take the derivative, sine, derivative is cos, and then plus cos alpha minus zeta by alpha, so cos alpha upon alpha. So that is, for that derivative, we'll get minus cos of alpha minus zeta by alpha square. When we take the derivative for 1 upon alpha, then when I take the derivative for cos, it becomes minus sine alpha minus zeta by alpha. So now we found out psi alpha and psi dash alpha. Now my ER simplifies as ER is equal to E0, 2 cos theta by alpha square psi alpha, and E theta is equal to minus E0 sin theta by alpha psi dash alpha. So now I have got simple expressions for E theta and E phi for writing their lines of forces. Now the equation for the lines of forces in the variable alpha is d alpha upon d theta is equal to alpha ER by E theta. We have found out what is ER, what is E theta, multiply that by with alpha, that will give us minus 2 cot theta psi alpha by psi dash alpha. So d alpha by d theta is equal to minus 2 cot theta psi alpha upon psi dash alpha. Right? Now for alpha, we can now write d by d theta log of psi alpha is equal to minus 2 cot theta, which is d by d theta of log sine square theta. I hope you can do it using mental mathematics or mental calculation. Using mental calculation, we can always do this. D by d theta log of psi alpha is equal to minus 2 cot theta d by d theta of log of sine square theta. Now from this we'll get d by d theta log of psi alpha sine square theta is equal to 0. So that implies psi alpha sine square theta is a constant. So that constant Q. Now what is that constant Q? That constant Q is my trump card that I will use later. But now for psi alpha, put the value sin j minus alpha minus j plus cos alpha minus j by alpha into sine square theta plus cos of my. So that is equal to sine of kr minus omega t by plus cos kr minus omega t upon kr whole into sine square theta. That will be equal to Q. Q is the trump card that I am going to use now. Now, what is Q? Q is a constant. Now, you remember that for lines of forces, how do you find out lines of forces? What in the E field, we find out the points where its phase is same. Then we connect those points and say the connecting curve is the lines of force. Right? Line of force, one line of force for E. So that is what we are going to do. So over that, Q is constant. Q is a constant. So over the lines of force, E remains value of E remains constant. So this is what I am going to do. So now ideal method is to find out the lines of forces. I have to solve for R in terms of theta. But this will be very complicated to solve using pen and paper, even using a computer. The closed form formula for this is not available. It is not possible also to find out a closed form formula. So what I'll do is I will resort to an alternative method. The alternative method is I'll write a program for the contour plot. How? With this assumption. Think of the line or the lines of force as a contour plot at different values of the constant Q. So each Q gives me one line of force. right? So we'll write a program for the contour plot. So if we write a program, we will get a graph. That graph will give me the lines of forces. Now for that graph, what I will do is I will take x and z distances in terms of lambda, right? So whatever is the distance, I will divide that by lambda. Remember this. So this is going to be useful for writing the program. X and z distances are in terms of lambda, and they extend to a value of my interest. So it can be 1 lambda, it can be 2 lambda, it can be 3 lambda, it can be 1.5 lambda. So whatever is your interest, extend them up to that value. Dipole will be depicted as a tiny source which is z directed at the origin of the coordinate system, right? So with these two in mind, we will look for a pseudo Matlab code. You can develop this Matlab code. I am going to give you most of the things from which you can write the Matlab code. First is fix a limit in terms of wavelength. So this is the plot limit. Limit on the plot in terms of wavelength. That is what I told you, along x and along y. So let me take the minimum value is RL will be 0.1, which means RL is equal to 0.1 lambda. Whatever will be lambda, that much will be multiplied. But if I normalize it for any lambda, it will work. Therefore, I am normalizing it. So RL is equal to 0.1. You can take it to be 0.125, 0.625, but don't take it to be 0. Because the moment you take it to be 0, you are coming to the origin where it will not exist. Field lines of force will not exist. Everything will blow up. Then upper limit on R. RU, I am taking 2.0. You can take any value you like. You can take 1 lambda, 1.5 lambda, etc. Whatever is you like. But I am taking it from 0.1 to 2.0. So this is my extension. Then once you have decided that you will extend up to this much distance and you extend up to that much distance. Now let me define in R and theta how many points I am going to consider. Phi we are not considering because it is phi symmetric. So in R and theta, how many points we are considering? So assume that in the R, we will consider 61 points. So NR is equal to number of points in R is equal to 61. And TST is number of points in theta, that is also equal to 61. And how many contour levels? Number of contours. How many contour levels? I am considering that is N is equal to 8. You can take it as NQ also, contour levels. So NQ is equal to 8 or N is equal to 8. We are considering 8 levels. So if we consider 8 levels, this will be that. Then where I will start in the time point. If you remember my first class, I told you we are for oscillating dipole, which was the second class after the radiating charge, after the accelerating charge, we considered oscillating charges. So in that case, we started at T is equal to 1/4 capital T or 0.125 times the time period. That is where we started. Starting point was minus of that. So I'll start from that point. So T is equal to 0.125. So from that I am starting. My capital T is equal to 1. So this is in terms of capital T, time period. So T is equal to 0.125 if my time period is 1. So normalized. Then D is equal to 2 pi into t. So I will define a d. D is equal to 2 pi into t. So this gives me, so at each, what is the time instant? T is equal to t upon 8, which is equal to 1.25. Now I will form a mesh grid of r and theta. Now what happens if I take, somehow suppose you are taking x, you are making a plot of x and y. How you will define x? Now suppose x exists at x is equal to 1, x is equal to 2. Y exists at y is equal to 1, y is equal to 2. Now if I write a program for that, for plotting, what you will do, at x is equal to 1, y is equal to 1, at x is equal to 2, y is equal to 2. This is a linear curve. But if I take a planar curve, at x is equal to 1, y can have two values, y1 and y2. Similarly, at x is equal to 2, y1, y2. Similarly, at y is equal to 1, x1, x2. At y is equal to 2, x1, y2, or x1, x2. Therefore, these are grid points. When you plot, making a 2D plot or a 3D plot, you require grid points. At each point on the grid, what will be the value? Then you combine them, those values, that will give you the required plot. For 1D, there are the grid points are only respect to x and y, one-dimensional x and one-dimensional y. For 2D, x becomes two-dimensional, y becomes two-dimensional. Therefore, in the Matlab, there is a program called, there is a function called mesh grid that easily converts r and theta to grid points. Now for that, what I have to do is, I have to define r and theta limit. So that I am doing mesh grid within bracket LIN space, which means linearly space r values from RL to RU in increments of NR, right? No, from RL to RU, total number is NR, right? So if RL is equal to 1, RL is equal to 5, NR is equal to 5, then they will be spaced at 1, 2, 3, 4, 5. But if I make NR is equal to 10, they will be 1, 1.5, 2, 2.5, 3, 3.5. So that way they will go up to 5. So NR determines the number of points, right? So based on the number of points, this will be equally divided. So the distance between 2 points will remain same. Similarly, for theta, theta will vary from 0 to pi. So 0 to pi, then NTST, number of points in theta. So once I do that, then I will find out alpha. We have defined what is alpha. Alpha is equal to KR. R we have taken already. For R we are taking here D. For each instant of time, we will find out a different D or different R. Therefore, we have taken D is equal to 2 pi T. So my alpha is equal to 2 pi into R. So alpha is equal to 2 pi R, which is in terms of lambda, R in terms of lambda. Then we define Z. Z is equal to R into cos theta, X is equal to R into sin theta. So these are transformation from Cartesian coordinate system to spherical coordinate system or polar coordinate system. So Z and X, Z in, from polar coordinate system to Cartesian coordinate system. In polar coordinate system, we had R and theta. In Cartesian, we have Z and X in this case. So Z is equal to R cos theta, X is equal to R sin theta. Already I have told you why this happens. Because I told you when the dipole is Z oriented, its R component is R cos theta, Z cos theta, theta component is minus sin theta. So from that it comes. Now write what will be Q. For Q, we have found out an expression. So use that expression. Here there is a small mistake. Q is equal to cos ALP minus T dot slash ALP, not U. This should be ALP. Right. So cos ALP minus T dot slash ALP. Now dot slash means division is by element to element. For example, I have a vector x is equal to 1, 2, 3, vector y is equal to 2, 3, 4. Right. Then x dot slash y means 1 by 2, 2 by 3, 3 by 4. So each element is divided by corresponding element. Right. Therefore, we are taking dot slash. Okay. Similarly, dot star is element by element multiplication. Why we are taking element by element multiplication and division? The reason is we are considering a grid. In the grid, each point is to be multiplied or divided by corresponding point in the corresponding grid. We cannot take a matrix multiplication. If I take a 3 cross 1 and 1 cross 3 matrix, that will give me a 3 cross 3 matrix. I don't need that. I need a 3 cross 1 matrix. So because of that, Q is equal to this. So this gives me the contour levels. Now to plot the contour, write contour of minus x to x. So that is the limit on x. Similarly, the limit on z, z to z, limit on q is q to q. And n is the level, number of levels. So number of levels we have defined earlier, n as 8. Now if I write this is a pseudocode. If I write a proper code and run it, I will see this. Now look at this. At the center is my dipole. Now dipole is clearly visible. From the dipole, you can see what happens to the lines of forces. They are gradually coming out, which is lines of forces are appearing from the dipole, then they are detaching, then they are reappearing. So there now you can see there is a yellow and there is blue. Yellow is one extreme, it goes to positive extreme yellow, it goes to the negative extreme blue. Right? So this is what we saw in the 3D also. In the 3D on the bottom plane, this was what was present. So this gives you a bird's eye overview of Hertzian dipole, and I complete Hertzian dipole here. Next class we'll start with small dipoles, then we'll move on to half-wave dipoles. We'll use the concepts of Hertzian dipoles there. So I hope you will remember what we discussed, or you will study what